Welcome back. Today's topic is Laplace and Poisson's equations, the two equations which are widely used in electromagnetic fields to determine electric field intensities, electric flux densities, and also potentials. In the last video lecture, we have discussed about the polarization in dielectrics, and we have also seen the boundary conditions at dielectric interfaces and how they help us to determine the electric field intensities, potentials, etc. when we traverse from one dielectric medium to another dielectric medium. And in this video lecture, we will see what actually are the Laplace and Poisson's equations. We'll try to develop the Laplace and Poisson's equations with respect to electromagnetic fields in this video lecture. I'll start with the Gauss Law. You know that the Gauss Law is equal to, it states that the surface integral of the normal component of electric flux density vector is equal to the charge enclosed by the surface. So d dot ds, or the surface integral, s is equal to q, or it can be written as so you know that d is nothing but, so if I substitute it here, I'll be getting, instead of flux density, I can employ electric field intensity. The only difference is that I'll be getting a medium here. Okay. Now, the same equations in their differential form are represented in this fashion. We have tried these. These are called as Maxwell's equations. Yeah. This is the Maxwell's first equation, or the differential form of Gauss law, in terms of flux density and in terms of field intensity. So this is the Gauss law, and we also know one more equation, the relation between voltage and electric fields, which is the equation which we have derived in the earlier case. V is the line integral over a line of the electric field intensity vector. Now, this in its differential form can be represented in this fashion. The gradient of voltage is the electric field intensity vector. Sorry, there must be a minus symbol here. Yeah, this is the minus symbol. Okay. So these two equations now I will employ now in order to develop Laplace equations and Poisson's equations. Yeah. So as already I have, this is my Gauss law in its differential format, and now I do have that gradient of V is nothing but E bar minus E bar, right? So if I employ here this particular equation, then so instead of E bar, what I'll keep this as gradient of V. So this is what I have placed here. So you know that divergence of a gradient is nothing but it is called as a Laplacian vector. This is called as Laplacian vector. Laplacian operator. Okay. Sorry, not a vector, it is a Laplacian operator. So Laplacian operator of V is nothing but this one. There will be a negative symbol also here. So my final equation is this one. Del square V is equal to minus rho V by epsilon. This is called as Poisson's equation. Poisson's equation. Yeah. See, there is a minus symbol here. Yeah. This is the Poisson's equation. Now there will be some special cases where rho V may be 0, which means that the volume charge density may be 0. In that case, what happens is, if I substitute rho V is equal to 0, then that equation will become del square V is equal to 0. This happens in a very special cases when there is a charge free region. So this equation is called as Laplace equation. So two equations which are generally employed to determine the fields. How to apply them, that we will see in the next video lecture. I hope that now you are able to identify what is a Poisson's equation and Laplace equation. They are very simple equations. Del square V is equal to minus rho V by epsilon, whereas del square V is equal to 0 if the region is a charge free region. and that particular Laplace equation, which we do have, del square V is equal to 0 in case of charge free region, right? If it is not charge free region, then that equation will become del square V is equal to minus rho B by epsilon, where epsilon is the absolute permittivity of any medium. So this Laplacian vector, it will be having different formats depending upon the coordinate system. See, this is this equation is for Cartesian coordinate system, and this equation is for cylindrical coordinate system, and this equation is for spherical coordinate system. Okay, so try to remember these equations which we have already learned in our first units. These are the representations of Laplacian vectors. Okay, so we will see in detail about these things in the next class, where we discuss problems of these things. Okay, so I hope now you are able to derive Laplace and Poisson's equations and write the Laplacian operator in different coordinate systems. Okay, so I'll ask one more question. What do you mean by Laplace equation and Poisson's equation, and why they are employed? You are supposed to pen down them. Thank you.